Welcome to today's chemistry lecture. In today's lecture, we will discuss the activity 17.1, which is about an experiment. An experiment that can be performed to show the increase in the rate of reaction with the increase in the concentration of hydraulic acid. So, let's see what will we learn in this activity. This experiment practically demonstrates how increasing the concentration of hydrochloric acid increases the overall rate of reaction when it will react with calcium carbonate or limestone. So let's see further the reaction activity. So the first step is experimental setup, which is shown in the figure 17.3. For this experiment we need apparatus. In apparatus we need a flat bottomed conical flask is fitted with a delivery tube. This tube connects directly to a gas syringe supported by a stand and lamp. The reactants that are required in this experiment is limestone granules added to the flask in excess, ensuring there is more than enough to fully react with all the acid. The second is hydrochloric acid. A fixed identical volume is used for each experimental trial. Next step is methodology and data collection. First is gas evolution. As soon as the reactions start, carbon dioxide gas is generated. How we measure? Measurements are: the escaping gas travels through the delivery tube and is collected into the gas syringe. The printed scale on the syringe barrel directly measures the volume of carbon dioxide gas evolved. How to control variable? By controlling variable to ensure a fair test, all other experimental variables must be kept strictly constant. How? Let's see. First step, total volume of the acid used. Second, temperature of the system. Third, initial mass and surface area, mean size of the limestone granules. Fourth is the rate of physical strain or agitation. All the variables will be controlled strictly to keep the experimental variable constant at every time. Let's do a comparative trial. The experiment is first carried out using 1 molar hydrochloride, tracking gas volume against time. The entire process is then repeated under the identical condition using a higher concentration, means 2 moles of hydrochloric acid. Now we'll interpret the rates of graphs. When the data is collected, a graph is plotted showing time, second or minutes on the x-axis versus volume of gas evolved on the y-axis. Let's interpret the paragraph figure 17.4 graph of reaction rate. Anatomy of a single reaction curve. The resulting graph is always in the form of a curve. The slope of this curve tells the immediate speed of reactions. For example, at start, the curve is at its steepest. This indicates a faster rate of reaction right at the beginning because the concentration of reactant particle is at its highest. After some time, as the time passes, the curve begins to bend and flatten out. This shows the reaction rate is slowing down because the reactant molecules are progressively being consumed, reducing their concentration. So, at the end, the curve becomes completely flat as a horizontal line. This means the reaction has stopped because the limiting reactant hydrochloric acid has been entirely used. By comparing two concentrations as shown in figure 17.5, when we plot the curves for curve A 1 molar HCl and curve B 2 molar HCl together, we observe clear differences as we see in curve B, where 2 molar of hydrochloric acid has been used. Features a much steeper initial slope compared to curve A. Curve A, 1 molar hydrochloric acid, features a gentler, slower initial slope. There's a huge difference between curve A and B. So, the conclusion and the summary of the graphical conclusion is higher concentration is equal to steeper curve. For example, the greater the starting concentration, the steeper the curve at the beginning of the experiment. Second, the kinetic mechanism. A more concentrated acid means there are more active particles per unit volume, which maximize the chance of effective collisions per second, resulting in a significantly faster reaction. Hopefully, you understand this lecture. See you in the next lecture.